holds a BA in environmental biology from Dartmouth and an MS and PhD in natural resource management from Cornell. 4 years with experience with New Jersey Department of Environmental Protection. He has some story about there where he learned the most about pollution remediation. I guess in New Jersey. But he has since gained 25 years of experience on a number of things. He was the former president of the North American Lake Management Society, and currently I believe is their editor of their peer-reviewed journal. Ken has come to us today to talk about what we can anticipate, what we should be concerned about with respect to lakes and climate change. Fortunately, it's not anything controversial, but we're looking forward to getting the science behind what we hear. So without any further ado, Dr. Ken Wagner.
Controller here, I just don't have the presentation. No, it's okay. You guys are doing the right things here. It really is good. A friend that I enticed to come from Wisconsin to Massachusetts to work with me in the 1980s eventually moved on as the executive director of the Cobbessy Watershed District up in Maine. And he was always telling me, send me pictures of all the bad stuff from further south so I convince people that they need to protect things. And that's your greatest challenge, and that's going to come up in this talk as well, is that fixing things, which is a lot of what I do in my profession, is actually a lot easier than protecting them. And the protection part is way more important. You know the old ounce of prevention is worth a pound of cure. It's critical that you stay in front of it. That's where the whole thing with invasive species, phosphorus loading, the whole thing. The catch here is we got a lot less control over climate change. You know, there's certainly things you can do, but there's limits to what anybody can do as an individual, and there's limits to how fast you turn around this huge steaming liner that, you know, it's not going to turn on a dime. So there's a lot of things to think about. The full disclosure here is I am not a climate scientist. Everything I'm going to tell you about climate change comes from other people's work. I've read up on this quite a bit. I even got some great slides off the EPA website before they took it down. But the part about what it means to your lake, that is where I've been working for 40 years now. So I'm very interested in that end, and I feel very qualified to explain what this means to a lake, so we'll take it from there. Okay, I'm going to show you a lot of slides today, but if you really need proof that there's climate change, this is it. It's Country Hans Pearl, a fairly famous limnologist from North Carolina, and it is unfortunately what you'll remember most from this talk. The important thing to understand with climate change is it isn't about little increments of change. It's about the variability around that change. Now, I'm going to give you a little bit of a statistics lecture. I'm not going to call it a lecture and get all the doors barred so nobody can get out. I'm not going to throw equations at you, a lot of heavy-duty math, but there's a lot involved. There's some basic statistical concepts you need to understand. It'll help you with a lot of things. Frankly, you do statistics every day of your life. You just don't realize you're doing it. Almost every one of you got in a four-wheeled vehicle and came over here yesterday or today. You know you could have been in a car crash. I mean, there was a finite probability. You thought this was worth it. I hope it is. But the point is you weighed those two. You looked at that distribution, probability distribution of possibly having a problem, cost, everything else that, no, this cost benefit, this is worth it. You do this stuff implicitly all the time. Do you look around the back of the door every morning when you come down to make sure there isn't somebody there with a knife? No, because the probability is infinitesimal, but it exists. You make decisions every day, what to purchase, where to go, and a lot of those relate to implicit statistical things, and hardly anything is a yes or no answer. Very little is. I mean, to this day, my wife of 39 years never actually said yes to my marriage proposal. Very little is yes or no. It's all distribution. And it's the spread, the tails, the mean, the mode, all that sort of stuff goes into it. And we just implicitly get this. Well, when you start dealing with real data, then you actually see it on paper. So, okay, I am not here to tell you why we have climate change or debate any of those issues. Anyone who tells you that it doesn't exist is ignoring data from literally thousands and thousands of years. And I'm not saying just recent stuff. I mean, here, this is the scale. The back, you can look at the other one. This is hundreds of thousands of years, cycles of carbon dioxide content. Of course they are. And now here, we're right at a peak of one. We should be starting to go into a colder period. However, we're there. So, okay, something has happened here that's different than in the past. And I'm not going to deal with that today. But the fact that there is climate change always going on, that there is somewhat of a cyclic pattern, is pretty much undeniable. The catch is, the change is often obscured by the variability around it, and that's the catch. And it's very insidious when you get graphs like this. This is showing the change since late 1800s to the present of the march of the average global temperature. Well, yeah, okay, but look at the scale. That's average over history. That's half a degree low, that's 3/4 of a degree high. We're talking about a total range for the average of minus 0.5 to plus 0.75. Who cares? That's nothing. I mean, if we change the temperature 2 degrees in here, you're not going to notice that. It's not a big deal. The average, but nothing lives in the average. Organisms don't live in the average. We don't live. If I can suck all the oxygen out of this room for 10 minutes, some people are saying that's what I'm doing, but, and then put twice as much back in for the next 10 minutes, the average is the same, but we're all dead. You have to live in the moment. And it sounds like a great philosophical thing. I mean, literally. And those fish have to live there. If there's no flow, no water, there's no fish. It doesn't matter if there's twice as much flow the next day. You have to have that sense of variability. It's the thresholds, it's the limits to what they can tolerate. Again, we're at one of those wonderful camps in New Hampshire that we had a presentation on last night. You go to take a shower after a wonderful day of outdoor activities, and there's 2 stalls. One of them, well, they both have an average temperature of 102 degrees Fahrenheit. Pretty comfy shower. One of them ranges from 101 to 103. The other one ranges from 40 degrees to 180, but the average is 102. It's fine, right? That's the problem. It isn't this little tweak of an average, it's the variability, because everything on this graph is an average for a year. There's no variability being shown. It's the variability you have to focus on. All right, not climate related, just illustration of this for statistical purposes. This is a graph of phosphorus content in sediment as you go into deeper and deeper water. You go out here to the lake, you see it's beautifully coarse with rock and sand and gravel near the edge. There's not a lot of available phosphorus in that. As you go out deeper, you will find muck. And in that organic muck, there's much more phosphorus. That's just a known phenomenon. However, what you often don't think about is we look at just this chunk right in here, there's not a lot of variability there either. We get out here where the number is bigger, there's quite a lot of variability. Clearly, the average out here is higher than the average here. But more importantly, the range is much larger. That's a statistical truth. As the mean goes up, the variability around the mean goes out. If you put things like standard deviation, a measure of distribution over the mean, you get something called coefficient of variation, and that just gives you a sense for what's going to happen. So as our temperature warms up, the range around it gets higher. And something as small as a half a degree change can translate into many degrees of more variability. And again, back to the showers analogy or the oxygen analogy, it's that range, it's the extremes that are getting us, not the little change in the average. The bottom graph, same idea. This is the classic chlorophyll versus phosphorus. Phosphorus being a key nutrient for lakes, chlorophyll being the common algal pigment in all algae. And yeah, as phosphorus goes up, so does chlorophyll. But this is a zillion points behind this sort of plate. You could have a pretty low chlorophyll with a pretty high phosphorus, and you could have a pretty high chlorophyll with a pretty low phosphorus. So if I only had 2 data points, I might not be able to make anything out of this, and I may draw a completely different conclusion. The greater the variability, the more data you need. That's why the monitoring is so important. It's critical to have that information. You've got to know what's going on out there, and the more variability there is, the more information you need to make sense out of it. You can't randomly pluck values out and expect you're going to understand what's going on. All right, so let's relate it to climate change. This is a cool, again, none of this is my work. This top graph is the snow cover over the year in the northern hemisphere. Kind of hard to graph it. How much of the area is covered by snow at any time? And the regression line, regression is a statistical technique where they draw a line that results in the least amount of differences from all the points going to the line. And sure enough, it goes down. If you looked at it without that line, yeah, you kind of see that it decreases, but there's quite a lot of scatter. There's more variability in some areas than others. Point is that it's hard to see a real line here without me drawing it because there's so much scatter. But if you break down the data and look at it month by month, we have August, September, October, November, and December. Now, of course, there's a lot less snow in August and September, and there's a lot more snow in November and December, and even bother with the winter months. But the important point, look at the variability. Not that much there. More than twice as much as you move into the winter. Again, it's the variability that's the issue, not the actual number. It may be important that it's warmer in the summer than in the winter. And yeah, of course there's going to be more snow in the winter. But how much more snow? Well, I don't know because the variability is so high. And that's where the stuff creeps in. So you have to look at a lot of different factors to sort this stuff out. So it gets complicated. And it's not fun. And everybody loves to have it that quick little yes and no snippets and all. And I've already told you, there's very few yes or no answers in life. Almost everything we run into problems with is because we're looking for yes or no answers to questions of gradient. It's how far do you push it? You know, how far do we extend the envelope? How tight can we really give a yes or no answer to a lot of this stuff? It's hard. All right, so what's actually happening? This is real data, not somebody's model projection. Over time, this has changed since 1901, so over 100 years worth, the colors represent the change in precipitation. So if you go to some place like the Southwest, they've got literally up to 20 to 30% less precipitation than they had 100 years ago. That's why they had droughts. In New England, interesting enough, we have more precipitation. We're not getting drier, we're getting wetter. Not wildly wetter, but we're getting wetter. So a lot of places, the gray is no change at all. So climate change doesn't mean it's unidirectional for everybody the same way. It means there's different patterns happening in different places, and it means different things depending upon where you are. If we were sitting in Arizona, this would be a very different talk. So now that we're in New England, we're looking at more precipitation. Funny, Vermont, of course, these are state by state. Vermont stands out as having more precipitation than anybody else. That's probably a couple of big storms they got hit with. But it's, you know, in general, you're looking at 10 to 20% increase. That's not huge. But how do we get that increase? It's actually fewer storms, but bigger storms. So we have more drought, and we have wetter wets and drier dries. That's the problem. More variability. All right, so what do we actually expect to get? Slight increase in the precipitation amount, warmer winters, which means less snow, more rain. So now it's going to go through the system faster, and you're not going to have that snowpack in the spring. Every year, it's going to vary. It's not going to be the same every year. You get highs and lows. We've had some great snow years lately. That's some really bad ones. Again, the variability jumps. And this is just a stream that I have worked on for 20 years. Those are all natural flows in it. Wildly different conditions over the range of typical variability. And of course, that's getting worse and worse as we experience the climate change. We're going to have shorter period of ice cover. We already do have that. Fewer but more intense storms. We get warmer summers, which leads to warmer water. Warmer water has a whole lot of consequences for organisms, and I'll come back to that. And then just greater variability. That's the problem, is dealing with uncertainty, dealing with variation. Think it's tough in a recreational lake? Try being a water supply with a reservoir, particularly a big supply where you've got to take a lot of water out of that reservoir every year. And you don't know if you've got enough. Was it South Africa that's looking at what they call day zero, where they run out of water, and it could happen? Did manage to prolong it now. The projection is now somewhere in July, but it could still happen. Keep in mind that's winter for them, so they get a chance there. This is a real threat. We live in a water-rich region. We are in way better shape in New England than most other places, but we still have dries. You all lived here in 2016? You know how dry that was. All right, so let's bring it home here, right out the window, Winnipesaukee. There are the ice out dates for Winnipesaukee over time. Ignore the line for a moment. Anybody really see anything there? I don't. It's a shotgun blast. Now, using polynomial regression, great fun. This is Mark Twain's line. There's lies, damn lies, and statistics. That's what we're looking at here. You know, you could see there was a decrease back in the late 1800s. We got another decrease recently. There's 2012 and 2016, the two earliest earliest ice outs ever. 2016 was the earliest, and I was up here when that happened. However, this doesn't go beyond that. This year we were back in the 20s of April, so now we've got a number way the heck up here. Again, increased variability. All right, so I don't know that you try to read too much into this. We all think the ice is going out earlier as a general thing, but when you look at the true history of this, we have some really lows there and we have some really highs there. Otherwise, it's just a big scatter. You need a lot of data to pick this sort of stuff up. Oops, went the wrong way. All right, so let's look at some other places that maybe have more or better data. Woods Hole Oceanographic Institute on Cape Cod has been keeping records for 100 plus years, 120 years. Very, very meticulous records. And if you look at everything before about 1960, you know, the annual's pretty flat, slight decrease in temperature. Summer definitely got colder. Winter got a little warmer. A lot of variability, not a lot going on there. I'm not impressed. But now we look at what's happened since about 1960. Pretty straight lines. It's still a lot of variability, but not annually, not really. That average is definitely going up and up and up. Well, when did things really start changing at Winnipesaukee? I showed you back to like 1890. What if we just sort of forget about everything before 1960 and just look at 1960 on? Oh, all right, still a lot of variability, but wow, we're looking at a 2-week shift in 50 to 60 years of having, you know, we're 2 weeks earlier on our ice out than we were 6 decades ago. That's almost 2 days a decade. Actually, the average that people looked at overall is 1 day per decade. So you're actually more, but it could be because it's a bigger lake. Real interesting. So it's real, and it really is only since about 1960. Every single thing I look at in climate change, the big changes are post-World War II, somewhere around 1961. And of course, people went into driving. I think impervious surface and development has a lot to do with it too. But again, I'm not here to discuss the why, only that it is. All right, so now we get to the part that I really know. What does it mean to your lake? Because I've been studying lakes for 40 years. I'm out on lakes all the time. I am not an office guy. I mean, I have to write the reports and deal with the data. I'm still a field guy. I actually quit my last job because they want me to stay in all the time. So I've been in the company so I can go out and play. And I go out and do a lot of stuff on lakes. And so I'm into this stuff. I see it for myself. 2012 was the first time I recorded a surface temperature reading of 30 degrees centigrade in a lake. And I've been doing this stuff in Massachusetts for 30 years. You know, I'd never seen a 30 degree, that's 89, 90 degrees at the surface, you know, upper foot of the lake. I'm sure other people have, but I never had. And now I've seen it more and more often. Although last year was pretty cool. It was, you know, not that hot. 2016 was very warm. But all right, these are the things that jump out. There's 7 key factors in lakes that I'm going to talk about. I'm going to talk about each one of them. Okay, so the flushing rate. It's becoming more variable. Classic example, this is a little pond, it's only an acre or two in Wellesley. The watershed is 417 times the size of the lake. I mean, a simple little rainstorm should just blow everything through there. And yet we couldn't get enough water in summer 2016 to flush this out with all the duckweed growing on it. It's just incredible drought. Not drought in the sense they think of in water supply, because it didn't last, you know, a long time like Southern California. It's just that it's a short burst or a prolonged period of dryness that has distinct consequences for the lake. The flip side, though, is one little storm, about a month after I took that one, in a different pond, also in Wellesley, and the entire thing is flushed multiple times and is brown and turbid with water. It's urban runoff. Not good. But the point is the variability is huge. It's like over in Vermont to say if you don't like the weather, wait a minute. Well, if you don't like the water quality in these places, maybe it's wait a few days, but it's going to change drastically because we've got higher highs and lower lows. Okay, variable water level. Now again, Winnipesaukee, it goes up or down a foot, I guess people get excited. Some lake over in Maine, Sebago, was used for power for years. They would drop to 5 foot and people were screaming. These variations, though, are very real. This is, again, a fairly small lake in Massachusetts. It doesn't have much of a water source, so when it went through summer of 2016, there wasn't a whole lot of lake left. And now in 2017, almost the exact same date, completely full because it was a much rainier summer. But that variability is huge. and there's nothing they can do about it. Well, actually there is. They're putting a well in to pump water in to actually keep the lake level up and counteract the evaporation. But I mean, these are you can't control the weather. That's a real problem. You also can't predict the weather very well. I mean, the weathermen get it right like 30% of the time. It's like being a hitter. You hit 300 and you're making $1 million. We're not very good at this. Okay, this is one that I think you really have to hone in on for your purpose, particularly for protection. This is just one example, but I have many of them, and I really believe in it. This is a lake I've worked on for years. That's a very tight relationship between annual rainfall and the phosphorus load. More rain, more stuff runs off, more stuff gets in your lake. Well, you can't really control how much it rains. So you need to control that land to make sure the stuff isn't getting off and getting in your lake. Because the more it rains, the more stuff you're going to get. You can't change this relationship, but you can change the slope of the line by managing the land better and keeping the stuff out of your lake. And of course, catastrophic things like that. This is literally from a 1-foot diameter stormwater pipe. That's all that took. Blew out this entire thing. And that's the delta that got formed in the lake where it is. It's pretty impressive what can happen from catastrophic things. So again, the extremes, that's the big issue. We're also likely to get more internal loading because things get warmer. I'll come back to that. That mix of intense storms and then prolonged dryness is a huge issue. That's like the worst case scenario is a wet spring followed by a dry, hot summer. That is tough on lakes. All right, another one, stratification. You understand the concept of just the wind, the sun puts heat into the water, the wind mixes to a certain depth, but at some point, the energy put in by the wind can't overcome the temperature gradient established, and you can't mix those layers. They're very, very stable. It's like having oil and water there. The deeper it stratifies, the more stable it will be down there. The higher it stratifies, the more chance a big windstorm could possibly turn it over or affect it. This is a lake I worked on where literally in 2008, they had this bloom of cyanobacteria, toxic form, right down at the thermocline. Stuff Sabina's in too. And the very next year, they had the same bloom, but the thermocline set up at only 5 meters instead of 8 meters. So you're looking at, 10-foot difference in where it was. Well, at 8 meters down, 26, 27 feet, the wind isn't going to touch that, and everything stayed put, and that eventually dissipated. The thermocline actually goes down in the fall, and they never had an issue. This one, unfortunately, mixed up, and 2 million mussels died from a toxic outbreak. Huge. All that was a difference in the way stratification set up, which was completely weather controlled, which is a function of climate. So you're going to, and again, it isn't that you can count on it being a shallower thermocline because it's warmer. It's really just that you're going to get more variability, and this can happen. Okay. This is the most insidious one, and I want you to look at this critically, skeptically, because this is only one example. I'm not sure I completely believe it myself, but the theory is correct. This is the temperature at the bottom of the lake. This is a pretty deep lake, versus the oxygen demand. A lot of good comes from having oxygen in your lake, and you really would love to have oxygen from the top to the bottom. But when they get that stratification, decomposition is still happening in the bottom, and the oxygen can't get there from the atmosphere very fast. So we tend to lose oxygen in the bottom of the lake over the course of the summer. If it's really bad, if you have more than 500 milligrams per square meter per day of demand, and don't worry about the units, just 500 on there, you could get low oxygen at the bottom and for some distance above it. But 500 is kind of the cutoff. If you get 1,000, you're going to get low oxygen. And it's gradually going to work its way up and probably take over most of the bottom layer by the end of summer. If you get to 2,000, you're going to have low oxygen right out of the gate, like May and June, and you're going to have no oxygen by sometime in July and forget about having a cold water fishery. So this is a really important range from 500 to 2,000. Well, this lake's never been at 500, at least not in geologic time, maybe in geologic time, not in my lifetime. But okay, it often hovers around 1,000. And there's low oxygen at the bottom, but there's 10 or 20 foot worth where the trout can still survive, cold water and enough oxygen in it. But when it's been warmer at the bottom, it creeps up towards that 2,000 level. So we have a range from marginally passable to horrible over a range of 3 centigrade degrees. That's less than 6 Fahrenheit degrees. That is a very narrow range to go from not great but okay oxygen loss to holy cow, we're losing all our trappers. 3 degrees, that's all it took. Now the general rule of thumb in physiology is every 10 degrees is a doubling in metabolism. So you would think you might see a doubling, since this is related to bacterial metabolism, the doubling would go with a 10-degree change. Not here, 3 degrees. Now, is this what happens in every lake? I don't know. But the point is, it can happen, it did happen here. Just a small change in warmth in that water is a huge difference to the oxygen regime. And now, beyond just being habitat for trout being lost or any cold water fish, you also now have more of the bottom being exposed to the low oxygen water, which means more interaction between the sediment and the overlying water, more release of phosphorus, more internal loading, more algae, which rains down and gives you more oxygen demand, and it's that never-ending horrible cycle that you get into. So this one really worries me a lot. I just don't know if it's as bad as this makes it out to be. Plankton. Okay, I'm an algae guy. Let's say by original training, I am a phycologist. That is not a psychologist with a lisp. It's somebody who studies algae. And I love doing that. That's what I did at Dartmouth College. I had a wonderful algae professor, Hannah Croasdale, taught me a tremendous amount about life beyond just algae. If you want to understand algal ecology, all you really need to understand is temperature. I mean, that's 90% of it. The food reserves that each type of algae stores are metabolized best at different temperatures. Diatoms and golden algae prefer cold. They store oils, they do best in cold water. Green algae store starches. They do best in moderate temperature water. Blue greens store sugars. They do best in warm water. Now there's some variation there too and some weird offshoots and such, but the bottom line is as the water gets warmer, you're going to go from diatoms to greens to blue greens. So right away, climate change that even is bumping things up 1/2 or 3/4 of a degree on average means there's going to be higher highs. You've got a greater probability of seeing blue greens. If you can keep that water really cold, chillers in your lake, I don't know, you can get away from the blue greens to a large degree. There's some other things you can do with nutrient ratios that will favor other things. But the bottom line is the warmer it gets, the more likely you are to have blue greens. So climate change is nailing us a bunch of ways. We're getting more intense storms that put more phosphorus in, and we're getting warmer water that favors blue greens. That's a real problem. Now, there's been legitimate questions of, are we really seeing more blooms, or are we just doing a better job of detecting them? And the answer is yes. It's both. But there are really good papers out there showing that we do, in fact, have more blooms than we used to. And it's more loading of nutrients, warmer temperatures. And the blue-green blooms, other things can bloom, but the blue-greens are the toughest because they tend to control their own buoyancy. They come to the top and you see them better. All right, winter plant survival. Not doing a lot with invasive species here, but I do think that's a huge, huge threat to the lakes. We are getting later freezing of lakes every year. It's about a day per decade. And as a result, some of these plants have more time to move around, to expand. Some of the invasive species are really good at taking advantage of that little extra time to get a foothold. Worse is the fact that we're getting the earlier thaws, because a lot of the invasive, the milfoil, for example, Eurasian invariable, don't even really die in the winter. They may go back to root crowns, but then they just lay down, and they come back really fast because they're not waiting for seeds to germinate. They're not waiting for a temperature change in light. They can get going as soon as possible. We have lakes that in 2016, when we really didn't have much of a winter, at least down in Massachusetts, that were already like summer conditions at the end of March. At a lake that we only harvest, we don't use herbicides. It was like trying to mow your lawn in August if you hadn't done it since June. I mean, it was just so thick. So this is a problem. We run into real issues with it. The earlier start for growth gives you denser plant assemblages, makes it harder to control. And a lot of the real nuisance species are very good at getting that early start. All right, they had a big climate and water conference in Europe a few years back. And I had very nice, a lot of papers in a journal called Water Research. And they came up with this set of conclusions that, okay, climate change is going to increase our external from the watershed and our internal from bottom sediments loads, phosphorus. We're going to have higher frequency of extreme events, higher highs, lower lows, more often. Changes are going to be induced by higher temperatures, like I mentioned with the blue-greens being favored. And we're going to have more variable water levels. What was the most critical action to take? And I thought that was fascinating. Reduce nutrient loading. Control the sources, improve the trapping capacity. It's the most important step that you could take. I mean, sure, all the personal things to try to minimize your impact on climate, but in reality, we're a drop in the bucket even in this whole room. But you can make a difference on that piece of land you control to minimize what gets off of it. All right, so how else do we counter the effects of climate change? Well, definitely protective watershed management. From everything I've said, you probably think that I'm a big advocate for watershed protection, and I am. But you'd be surprised. You go to conferences and hear me talk about in-lake management, which is what I'll be doing at lunch, and people think I don't think anything at all watershed management. That's because most of what I do is fix lakes, not protect them. When you're fixing lakes, it's very hard to do that in the watershed. That's like having a leak in your boat and patching the leak, but never bailing out the boat. It's still not going to work. You have to take care of what happened in the lake. You get an invasive species in your lake. You can't fix that by doing something in the watershed. You know, you get a tremendous phosphorus load and it's now internally recycling. That's great if you fix the watershed so it doesn't happen again, but you still have the problem in the lake. So I'm very big on in-lake management as an integral part of the whole thing. But that doesn't change the fact that if you're trying to protect a lake, you have to be working in the watershed. It's the most critical thing you can do. So that's one. Runoff storage capacity. Holding runoff as much as you can, infiltrating it, doing things to clean it up. Phosphorus inactivation. You can actually take the phosphorus out of the water just like they do in water and wastewater treatment plants, either in the lake or in the tributaries. Circulation and oxidation. How you circulate, how you oxidate can have negative consequences. But getting more oxygen in the water can never be a bad thing. Having higher oxygen is good. Weed control efforts, anything we can do to control nuisance species, particularly invasives, they are wreaking havoc on us. So, all right, a little bit about each one. Protective watershed management. I am here to tell you there is no way you can make land that looks like this behave like land like that. It can't be done. And I will tell you there's government agencies, not New Hampshire, who have told people, oh yeah, all you need is watershed management, you can fix any lake problem. Nonsense. I have a bunch of other terms for that, they're all 4 letters. You know, you've got to manage the watershed, you can only tolerate a certain amount of development. I can tell you that the answer, we know this from lots and lots of studies. Once you get more than about 10% of the watershed developed, you're going to see some water quality issues. They're manageable, but you'll see them. Once you get to 30% developed, you almost have no prayer. I mean, there's no way you can stop stuff from getting in at 30% developed, even with the best BMPs. The basic rule of thumb is every change from natural landscape to developed or agricultural is going to be a 10-fold increase in phosphorus loading, minimum. Best application of all the BMPs we can come up with is going to average a 50% reduction. Half of 10-fold is 5-fold. It's still huge. It's a losing game. Now, you keep it down to a lower level, you're not quite so developed, you get things disconnected so that things aren't running right into the streams and into the lake, you can make a world of difference. I'm not saying the watershed efforts are futile, even in the developed watersheds. I'm only saying you're never going to get back to where you were before you developed. Early in my career, I was asked by a group, if there was one thing we could do for our lake, what would it be? I said, move out of the watershed. All right, well, if there were 2 things, what would they be? We love our lakes to death. So it's critical that you pay attention to what's going on in the watershed, but recognize there are limits to what you can do. Runoff storage capacity, again, I'm big into low impact development stuff, rain garden, simple stuff you can do on your own property. Anything you do to infiltrate, the absolute maximum phosphorus control is by infiltrating the water, making it go through soil. It'll absorb onto that soil. It's not an endless source of remediation, but it's darn good. But you can do a lot of other things. There's technical aspects of different types of detention basins. I've always loved this approach. It's just a big gravel-filled basin. The water goes in there, it infiltrates, and when it drops to the level of the gravel, that gravel does amazing thing with bacterial communities in terms of cleaning the water, and also because you don't have any open water, there's no mosquitoes, there's a whole lot of good things. It's simple, it's so simple. You do not have to have a lot of heavy-duty engineering. Phosphorus inactivation, I will be leaving on Sunday to go to Maine to do a big project up in the Belgrade area. It's where the solitudes out there, they're the actual vendors that are going to do the actual treatment. We're inactivating the phosphorus on the bottom of the lake that's been so green for so long. And it's just stuff accumulated over many, many years. We're going to try to put it back to where it was. This is something I've done with quite a few lakes. I've written papers about it. It is not as good as controlling it at the source in the watershed. But boy, if you've got that leaky boat and you patch the leak and you've got to bail out the water, this is how you bail out the phosphorus. You inactivate it in place. So it's another way to go about it. It also works really well for stormwater, and you can treat the stormwater coming in. I have an urban lake in Massachusetts that used to have 3 to 4 foot visibility. They used a ton of copper. They often had to close their beach. We've been treating the 2 main inlets for almost 10 years now, and their average visibility is over 15 feet, and they are thrilled. They're just great guys. Are going to spend $500,000 this year renovating the beach complex because they don't have enough room for all the people who want to come there. So you can do things with it. Is it philosophically very satisfying that we're fixing the lousy water coming into the lake instead of fixing it up in the watershed? No. But they don't have any control. Most of the watershed's the next town up. They don't have any control over that. So there's jurisdictional issues. Circulation and oxidation. There's a lot of ways to do this. There's 3 ways to circulate, and there's 4 ways to oxygenate without circulation. I've written an entire manual, 300 pages on this for the drinking water industry. It's highly complicated stuff. It sounds like it should be so simple. It's not. But the bottom line is having more oxygen in your water, particularly in your deep water, is always a good thing. How you get it there may or may not have negative consequences, but if you can make it happen, it's worth it. And weed control efforts. You need every technique in the book. I will say New Hampshire is very good about not restricting what gets done as long as it's reasonable application. There are states, over in Vermont, you're not allowed to use a drawdown. It's nonsense. And then one of their worst problems is ice damage to the shorelines. Duh. Down our way, you have to get a permit. And they're all done by local conservation commissions who may or may not like the technique. Usually drawdowns are fine. It's herbicides they don't like. Again, Maine and New Hampshire are pretty good about recognizing I've got an invasive problem. I'm going to do everything short of a nuclear strike to get rid of it, and that's the right way to approach it. I have a lake in Massachusetts that has zebra mussels. It is the only lake in Massachusetts with zebra mussels, and I cannot get a permit to do anything about it because there's an endangered snail that might be hurt, and there's a wetland that might be hurt. We have all these laws that protect things, but nothing that says we have to fix something once we've screwed it up. There's a real problem there at the government level, and I will say that New Hampshire is better than most. And you guys need this voice with New Hampshire lakes to keep pushing it in that direction. Okay, that winds up what I have to say on those topics. I don't do them for time. I can take a few questions if you like. Okay, great.
Questions. I wonder if you wouldn't mind standing up.
Definitely project so everybody can
Okay, so when there was phosphorus going in the lake because of septic systems, we built a sewer. And the sewer allowed a lot of development to happen.
Yep.
Did we fix anything?
What was the last line?
Did we fix anything?
Yeah, that's a good question.
You could repeat the question.
Yeah, okay, the question is if they had problems with septic systems contributing phosphorus to the lakes, they put in a sewer, which then allowed more development. Did they really fix anything? Of course, it's obviously got to be looked at case by case. I don't know the details of it. The gut reaction.
You're sitting on one right here.
Okay, well, the gut reaction will be no, because when you build out all that development, if they didn't also have covenants to restrict, you do have shoreline zoning, but worry about fertilizers and things like that. The other problem is, although you absolutely could have problems with septic systems contributing to lakes, they are not the threat that they often get made out to be. Now again, I can't speak to that specific circumstance. If you're in very sandy soil or very rocky soil with a lot of fissures, they are a threat. If you're in a more loamy or clay soil, they're not. So it depends on where you are and what's going on. I don't think it's so much bad that they put sewers in to get rid of the septic systems as you point, it then allows more development. And unless that development is carefully controlled, you can do just as much damage to the lake, yes.
You have a question, John, did you have a question in the back?
Yeah, just will a copy of the slides be made available to attendees?
They'll be on our website.
Yeah, the presentation will be put on the website, sure.
Thank you.
Question here, sir.
Could you give a brief review again of internal phosphorus loading at the bottom and why it gets worse when there's less oxygen? I didn't quite understand that.
Sure. Stand by the mic. The transfer of phosphorus from the bottom sediments back into the water column can happen multiple ways, but the biggest source is when you lose oxygen at the bottom, there are chemical reactions that go on, and a lot of that phosphorus is bound onto iron, and the phosphorus and the iron dissociate and go back in the water column. Now, from a water supply perspective, they're more worried about the iron. They don't want that in the drinking water. But from a recreational lake perspective, you don't want the phosphorus because it can fuel algae. The amount that comes out is a function of how much is in the sediment and the exposure to low oxygen. So as you start losing your oxygen and that interface of no oxygen rises in the water column, more and more bottom area is pulled into it and could be affected. Lake Auburn in Lewiston, Auburn, Maine, across the border there, was an unfiltered drinking water supply. They were doing great for years and years, but their lake looks like an inverted witch's hat, and the anoxia was always down in the deep part of the cone, and it was never a very big percentage of the lake, so it didn't matter. But that oxygen interface worked its way up, and it finally spilled out of the cone and onto the brim, and now they have a huge percentage of the lake that's exposed to low oxygen. Phosphorus came out, horrible blue-green bloom, and now people are drinking that water because they don't have any treatment. Now, it only happened 2 years, and then it went back to what it was before, and they've been building a war chest for rate increases so they can do something about it the next time around. But that's the kind of thing that happens. And once you get the oxygen low at the bottom, it tends to be a self-sustaining cycle that gets worse and worse and worse. You can put oxygen in and counter it, and what you hear from, well, yeah, but that's like putting our lake on life support. But the reality is if you counter it for a while, a decade or so, you will actually reduce the overall oxygen demand and push it back to something it was before. And you may not be able to stop, but you'll be able to do a lot less of it. So I don't know, is life support better than letting them die? I don't know. But that whole interface between oxygen and the bottom sediments is really important to the internal loading. So you really want the most oxygen you can get at the bottom, and if you're going to have an oxia, over the least area you can get it. Does that make sense out of it? Thank you.
Time for one more question. Bob?
To what extent are the lakes, the freshwater lakes in New Hampshire, absorbing CO2 from the atmosphere? I gather the oceans are a huge sink for CO2. Is that also true with freshwater? And if so, does it have any impact?
It's
Percentage
such
of
a
CO2 in the atmosphere have an impact in our lakes in some way?
Okay. The question was that freshwater lakes are absorbing CO2 just like oceans are. Is that a significant amount, and does it have an impact on the lakes? The lakes are so small relative to the ocean area that it really is a drop in the bucket. But yes, there is an impact in that if you have more CO2 in the water column, the acidity is higher, you get lower pH, and you'll have potential for more algae to use that carbon if there's adequate nutrients to go with it. Carbon won't be limiting. The good news is the more acidic, the less likely you are to get blue-greens. They like bicarbonate instead of carbon dioxide, so more acidic conditions actually are a bit of a hedge against blue-greens. But I'm not sure I'd put a lot of carbon dioxide in my lake for that reason. All right.
Thank you so much.
Okay.
So hold on, if you would, just for another couple of minutes, we'll just